Hello, everybody. So today we're going to continue our conversation on entropies by looking at how temperature can influence the entropy of a system. So we can examine how entropy changes with temperature by going to our good old definition equation of entropy as being the derivative of the minimum amount of heat needed to drive a process divided by the temperature of the system. Now, one of the problems that we end up getting into is the fact that the heat and temperature themselves are going to be linked. So one of the ways around this, and to help simplify this integral, is to realize that the heat transfer is going to be related to the heat capacity of the system and the change in temperature. And so by doing this, we can essentially help pull out the heat capacity. And if the heat capacity is constant with temperature, which it often is under a small temperature regime, the heat capacity comes out front and we get the change in entropy being related to the heat capacity of the system times the natural log of the ratio of the temperature difference. Now, again, we run into some issues because this is the general heat capacity. And most of the time, this isn't going to be exactly the most useful form. Because again, we don't know what the exact heat capacity is for a lot of systems. And so we often are forced to use this unsimplified integral. But we can simplify our system by doing our usual, which is essentially applying a set of constraints. So for example, if we examine isobaric conditions, well, then we get very lucky because our heat capacity now becomes our isobaric heat capacity. And similarly for isochoric conditions, our heat capacity becomes the isochoric heat capacity. So again, one of the things you should be very aware of when you're playing around with entropy is that the change of entropy with temperature is going to very much rely whether you're using isobaric or isochoric conditions. And unfortunately, if you're under neither regime, you're often going to run into trouble because you won't know the form of the heat capacity. And at which point, you're probably best off to essentially make use of the fact that entropy is a state function, and you can change the examine the entropy change with temperature under isobaric conditions, and then use our previous set of equations to examine the isothermal change of entropy with pressure. And so by putting these together, you can really examine the full details of the change of entropy of a system. Now, a lot of the times I'm not going to be concerned with just the entropy change of heating or cooling a system. I'm often going to be concerned with what we call combined processes. So this is, say, the idea that I may have a solid that I'm going to end up heating to make a gas. Well, in order to examine the entropy of this system, well, I'm going to need to essentially tie together several of the equations that we've used so far. So I can say start at my initial temperature and examine how the entropy increases as I heat to the fusion point. So essentially the point at which it starts melting. At this point, we run into essentially a different set of equations where now the entropy is going to increase under an isothermal phase change. So at this point, temperature will not change, and so I'll be looking at just the temperature of fusion, but the entropy is going to increase as I go from a ordered solid to a much more disordered liquid. And then using the heat capacity of the liquid, I can examine how entropy changes with temperature, and then again, examine the entropy of the phase change, which is again an isothermal process. So at this point, we'd be looking at the boiling point or the vaporization temperature. And then again, we can examine how the entropy changes as we heat this gas. And using this essentially nice set of equations, or essentially processes, it really is going to allow us to examine entropy changes for anywhere ranging from a solid to a gas, to a solid to a liquid, or even just from a solid to a solid by picking which chunks of the equation we're most interested in. And again, this does end up showing us several major features, which again, most of this isn't too surprising. As I heat a system, so as I put more heat into the system, it's going to become much more disorganized due to that extra thermal motion, and there's going to be a lot more available states. And as such, we tend to see a constant entropy increase as we go to higher temperatures, whether it's through phase changes or just through heating. But the contrast of this is that if I cool down my system, I'm going to restrict the number of states my system can occupy until and so it will subsequently lose entropy. But this brings us to a really important question of what's going to be the thermal disorder at 0 degrees Kelvin. So at 0 degrees Kelvin, well, at this point, I have literally removed all kinetic energy from the system. So this brings us to what's called the Nernst heat theorem, which again which shows that as I approach 0 Kelvin and I remove all kinetic energy from the system, well, my entropy is also going to drop to 0. And you can also imagine this based on the Boltzmann equation, where the probability of occupying a state is going to be related to the temperature of the system. And it turns out that if I have no temperature, I will only occupy the ground state or the lowest energy state. Well, if I only have one state, then I don't have any entropy. And this is essentially the third law of thermodynamics. So it's a little less flashy than the first two, but is it in fact quite important in essentially helping maintain our bookkeeping. And essentially states that the entropy of a perfect crystalline substance at 0 degrees Kelvin is going to be 0. So what this is again really telling us is that if I have a perfect crystalline substance, so this means I have a solid that has a perfect lattice, so it's going to be the lowest energy species, well, then I'm only going to have a single configuration. Well, if I only have a single configuration, then the natural log of that value is going to just be 0. So I have an entropy of 0. And it essentially all comes from the available microstates. But again, one of the important things to remember is this assumes a perfect crystalline lattice where we only have one single state. Now, you can imagine, say, if I have something like CO2, carbon monoxide, which can have two different configurations, carbon, oxygen, versus oxygen, carbon, carbon, oxygen, well, then I might have two different states that are equal in energy. Well, at that point, I'm going to have a non-zero entropy at 0 Kelvin because it would be the Boltzmann constant times natural log of 2. So again, it is also very important to remember this perfect crystalline part. But again, one of the other important things to make note of is the fact that, well, it's kind of hard to remove all kinetic energy from a system. So we're going to see some kind of odd behavior of our system as we start approaching this 0 Kelvin point. And this becomes particularly troublesome because based on our previous equations, in order to to be able to connect our entropy at, say, a relatively high temperature, like maybe 200 Kelvin, to essentially this low temperature version, I'm going to need to know the heat capacity at every temperature in between. And my heat capacity will in fact get a little bit weird as I get, say, below about 50 or 60 Kelvin. And so the reason why we start seeing some of these odd behaviors of our heat capacity turns out to be due to, well, quantum mechanics and its weirdness. So instead of trying to deal with the oddities of low temperature heat capacities, we often use a certain set of approximations. So a common one is called the Debye extrapolation. So what the Debye extrapolation essentially gives us is approximate temperature dependent heat capacity that is related to the cube of the temperature of the system and essentially an experimentally fitted parameter. So when you're trying to determine the heat capacities for these low temperature solids, we're often not going to use the traditional heat capacity you're going to look up in a table, which is often much more oriented towards, say, the heat capacity at uh, room temperature. Instead, we're going to need to make much more use of our fitted Debye parameters. Now, using this fitted Debye parameter, it allows us to develop what's called our third law entropies. So we can again make use of what we know of combining entropic processes. So I can determine the entropy of a substance at any temperature by essentially adding together our relevant terms. So first of all, we know that the entropy at 0 degrees Kelvin should be 0, or potentially another value depending on the non-crystalline behavior of our solid. And then we can essentially use our Debye extrapolation to get us to essentially another value at which we can switch over to the heat capacities that are much more reasonably provided by our by a Shamaty equation of the solid behavior. After this point, we can then get back to our usual values of basing it on the enthalpy of fusion and vaporization and the heat capacities of our liquids and gases. But again, being aware of kind of this odd behavior under the low temperature limit is actually quite important. This is also one of the reasons why, in practice, third law entropies are often provided for some set value, either at, say, room temperature, where you may be a solid, liquid, or gas, or they're provided at some low temperature region once you've exited the Debye region. And by using these third law entropy values at one of these relevant temperatures, you can then use what you know of the temperature dependence of entropy to work your way down to the entropy of a substance at whatever temperature you care about. So this actually gives us a lot of information of how to determine the entropies of individual substances. However, next time, we're going to get back into some real chemistry and talk about the entropies of chemical reactions. Till then, take care.